take a look at the last part of section 6.3. So we've talked a little bit about graphing sine and cosine functions. So I want to just go through each one of them quickly. We're not going to do an example, but just maybe what an equation looks like for them. And we also have to remember that when we do transformations, they always have to follow a certain order. And this is the order. Okay, if we don't follow that order, then what will happen is it will come out with a different answer. Okay, so let's start with the phase shift, okay, horizontal shift. What type of arithmetic is involved anytime that you do a shift? Yep.
Addition or subtraction?
Yep, addition or subtraction. And is the addition or subtraction inside the argument, or is it on the outside? Yep, it would be inside. Any kind of horizontal shift is adding or subtracting inside. So an example would be something like that. That would shift it pi units, and plus would shift it to the, which way does plus shift it? Yep, so. Yeah, plus is going to shift it right, left, and minus would shift it to the, about Raj? Right. Yeah, would shift it to the right. Okay, so it's exactly the same as the transformations we've done all year. Okay, period change. That's a horizontal stretch or compression. What kind of arithmetic is involved when we do a stretch? Yes?
Multiplication.
Multiplication. So multiplication is the stretch, and it's horizontal. So would it be inside or outside?
If it's a horizontal change, it would be inside.
Inside, yep. So something like y equals cosine 3x. That is a period change. What would the 3 do? How would you describe the original versus putting in a 3? Yep, Jackson.
To compress it by a scale of 1/3.
So that's kind of like saying a double negative. You said compressed by a fraction. Could you say it? Could you say it a different way for me?
Stretch it by a factor of 1/3.
Okay. Yes, that is correct, but not equivalent to what you said originally. Compressing it by 1/3. So compressing it makes it smaller, and we're compressing it by 1/3 because when we do a horizontal, it's always the reciprocal of the number in front of the x. So this would make it 3 times smaller. All right. So it's going to be 1/3 the size. Any question on that? All right. Amplitude change. Okay, that's another stretch. So when we stretch the amplitude, we're changing the height. Okay, that's a vertical stretch or compression. Multiplication again, because it's a stretch. But where would the multiplication be this time? Yep.
It would be outside.
It would be outside. So something like y equals 4 sine x. Okay, and what that does is it changes the distance from the midline of the wave, or that center line, to the height. It would now be 4 times as tall, 4 times as far away. Okay, and last one, vertical shift. So we said shifting earlier is adding or subtracting. Where would the addition or subtraction be if it's a vertical shift? Yeah.
On the outside.
Yep, it'd be on the outside. So I'm just using sine and cosine interchangeably because it works exactly the same for both. So we could have something like cosine x minus 2. That's a vertical shift. What would the minus 2 do? Would it move it 2 units up or 2 units down? Yeah.
2 units down.
That would move it 2 units down. Yeah. Minus is down, positive is up. Okay. And if you want to match up what we just did to kind of a generic equation would look something like there's all your different transformations in the order that you would do them. Phase shift comes first, period change or horizontal stretch is second, amplitude change is third, vertical shift is fourth. That's why I use the letters A, B, C, D, alphabetical order. Okay, so now we'll go through graphing a couple multi-step. So when we graph, remember two things we got to do. Find the table, which should have 5 coordinates, 10 different numbers in it, and then make a sketch. Okay, let's start with this one. Okay, how many transformations do we have in this one? Vanessa? Yeah, we have 2. Can someone remind me, what kind of transformation is the pi over 2? Yep.
Horizontal shift.
Yep, that's going to be a horizontal shift. And what about the times 2 in front? Yeah.
Vertical stretch.
That's a vertical stretch. So we've got a horizontal shift and we've got a vertical stretch. So we've got transformation, I called it 1 and 3. So we're going to do 1 first, and then we're going to do 3. All right, so let's make a table. Now, normally what we do is we put the original values inside the table that are not changing. Well, everything's changing. Nothing is going to stay the same. X column changes and the Y column changes. So I'll make my table, but all the original values are going to go on the outside. Let's put those first. What are the 5 original X values for sine? They're the 5 equally spaced values at the quarter points. Yep.
Pi over 2. Pi. 3 pi over 2. 2 pi.
And one more original value.
Pi over 4.
No, not
0.
0, yeah. Okay, so those are the original X's. We need to transform them, which I'll do in a second. And now I need my original Y's. What are the original Y values for the first positive cycle of sine? Lens?
Would it be 0, 1, 0, -1, 0?
Yep. So that's what we're going to base everything off of. And we're going to do the period change first, and then we'll do the vertical stretch second. What am I going to do to all of these X values? They all need to be modified. Yep. Okay, so if we add the pi over 2 to the X values, what happens to all the X values? They're all going to get what? They would all get bigger. If X values get bigger, which way is the coordinate moving? Like if you just take any coordinate and make the X value bigger, which way does it go? Yeah, it would go to the right. When we add, which way is the graph supposed to go? Yeah, it's supposed to go to the left. So we can't make all these X values bigger. It would go the wrong way. Do you have a second thought what we might want to do? We're going to subtract. Yep, so subtract pi over 2 from all these x values. So negative pi over 2, 0, pi over 2, pi, 3 pi over 2. Okay, at this point, we should be kind of comfortable with pi over 2's, pi's, and pi over 4's doing that arithmetic. Okay? You don't really want to have to be finding common denominators 5 times and all that. It's going to take a long time. All right, so we got our x's. Now we need the new y values. Okay. What am I going to do to my old y values to get the new y values? Nick?
Multiply over by 2.
Yeah. Okay, so that's going to be easier arithmetic. It's always easier arithmetic when we're transforming the y's. Okay, so we're going to get 0, 2, 0, negative 2, and back to 0. That's it. That's our table. So remember the way that this would be graded. You get 1 point for each x and y value you get right in the table. The entire table would just be a short answer question. You just click in each box and type the number in the table. To type a pi symbol, it'll pop up in pair assessment for you. Any questions on the table? Okay, let's do our sketch. So for y's, I need to go as high as 2 and as low as negative 2. So I'm just going to scale my graph paper because that's the amount of space I have to work with. And I need one value that's in the negatives. Everything else is 0 and up. And remember, these are all equally spaced. So you can use those as your labels on your graph. Because when you label things, you have to use equally spaced labels. So we've got negative pi over 2, 0, pi over 2, pi, 3 pi over 2. Okay, let's make our sketch. So negative pi over 2, we're at 0, 2, 0, negative 2, back to 0. Okay, remember, these are sine and cosine waves, sinusoidal functions, so there are no sharp turns on them. Should look just like that. Okay, any question on that one? All right, let's try another one. So let's try 3 cosine 2x plus 1. Okay, how many transformations here? Yep, 3. Yep, there's 3. Now the order is really important. If you have 3 transformations, that means you definitely have 2 on the same axis. Okay. The last problem, technically the order was not important because one transformation affected the x, one transformation affected the y. We actually did 2 totally separate things. Here, we're doing 2 transformations that are going to affect the y's. So if you take a number and you times 3 and add 1, or you add 1 and times 3, you won't get the same answer all of the time. All right, so now the y-axis, it's very important we do the correct order. Okay, so again, I'm going to start with my original values. For the x's, the original values are the same. Zero, 90, 180, 270, 360, each quarter point in the cycle. Y's are different. Can somebody tell me my original y values in the first positive cycle of cosine? Yep.
1, 0, 8.
Right. Okay. Remember, those aren't the only y values. We're only graphing one cycle because if I had to graph more, I could just continue this pattern down. 0, negative 1, 0, 1. Just keep continuing it and graph more. All right, let's start with the x's. What number here is going to be the number that we use to modify the x's? The 1, the 2, or the 3? Yeah?
2.
Yes, we use the 2. Can you tell me how we use the 2?
You would. We'd have to divide x by the value of 2.
Right, we're going to divide all the x's by 2. Or if you don't want to think of it as dividing by 2, think of it as taking half. So we're going to take half of everything. That gives us 0, pi over 4, pi over 2, 3 pi over 4, and pi. That's what you get when you divide all the x's by 2. Yes?
Why would we divide and not multiply?
Because remember, the bigger you make this number, the more squished the graph is supposed to get. So I need to take all these values, and squishing them means basically to make them smaller. So if you multiplied them by 2, that would make them all bigger, and it would stretch them out. The only reason we would multiply these by 2 is if you had this problem, 1/2 x. Now you would multiply everything by 2. Okay, and now y values. We know the 3 and the 1. We have to use both of them. Can anybody tell me what I'm going to do to all the y values, but also tell me the order I need to do it in? Like times this plus this. Or just, I need the right order. Yeah? Right. We always do the stretch first, then the shift. So we're going to times 3. So put that in parentheses. Think you're going to do that first. Then you're going to add 1. All right. What will my new y values be? Yep.
4, 1, -2, 1,
4, 1. You said -2, 1, 4. That all looks good to me. Okay. Any question on the table? Okay. So now let's look at our graph. We've got to go up to 4, and we've got to go down to -2. Okay, what I think I might do here is I need one more line. Let's put this up top. I guess kind of like that. Spacing's not that great. Oh. All right, so we got to go up to 4. So this will be 0, 2, 4. And we've got to go down to -2. Okay, looking at the x labels, I don't need any on the negatives. Are all these x's equally spaced? Ethan, what do you think? Are they all equally spaced?
Yeah.
Yeah, they don't look, because we have different denominators, but this is 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Yeah, they're all spaced every 45 degrees. So let's use those as our labels. When I said the pattern, I said it as 1 pi over 4, 2 pi over 4, 3 pi over 4, so you'd see it. But I am going to reduce anything that can be reduced, so I'll have the same values that are in that x column. All right, so 0, pi over 4, pi over 2, pi over 4, and pi. All right, let's graph our points. So we've got 0, 4. Pi over 4, we are at 1. Pi, we are at, pi over 2, we are at -2. 3 pi over 4, we're back at 1. And pi, back at 4. And remember, this is a wave, so it should have a curve to it. Just like that. The fancy name for this point that I just did in blue, and this point in blue, it's called an inflection point. It's the part of the graph where the curvature switches. There's two types of curvature to a graph. There's concave down, and then there's concave up. To think of concave up, think of it as like something that would hold water if you poured water in it. Concave down, it would fall out. So in this part of the graph, it's concave up because it would hold water from here to here. And then the next part of the graph from here to here is concave down. And then the next part after that is concave up and then concave down again. So it's called a point of inflection. In calculus, you learn how you can find that point exactly. We can find it because it lands on a nice grid line. But if it didn't, there's a way you can find it with calculus, but not in pre-calc. Right. Any question on that one? Okay. This is just another multi-step transformation. Anyone feel like we need another multi-step problem? Okay. So now, that's pretty much it for graphing by hand. Okay, so we graphed all the individual transformations last academic week. We did multi-step this week. Now we're going to start doing some things on the calculator. All right, it says find a complete graph, which means on the calculator. Tell me the window, and then find the domain, range, amplitude, and period. We actually should be able to do most of that before we even do the graph. Let's see what we can do. Okay, let's start with the domain. It doesn't matter what kind of transformation you do to a sine or a cosine function. What's the domain? What? All real numbers. Sine and cosine are they're the only two trig functions we've really studied in depth so far, but they do have domains of all real numbers. The tangent, the cotangent, the secant, and the cosecant do not. Okay, we're going to talk more about those maybe later today, tomorrow. See what we get to. But yeah, domain is all reals. Okay. Range. What is the range normally for the sine function or the cosine function? They have the same range. Yep.
-1, 1.
It would normally be -1 to 1. Have you done anything in that equation that would modify the height? How about Marin? Have we done anything that would modify the height? Right, we've multiplied it by 4. So the range here is no longer -1 to 1. What would the new range be after we take into account that transformation right there? Yep.
-4, 4.
It would be -4 to 4. And do we actually hit the -4 and the 4?
Yeah, we would hit those values.
We do. Which means we need brackets. Okay, amplitude. Now, you can't always assume that the amplitude and the highest value in the range are the same. If you look at this problem, the center line for this one, it's a little thicker than I need. The center line for this one is right here. The amplitude is 3. Okay? That's the highest that the wave goes off of the center line, from 1 to 4. That's a measurement of 3. But the highest value is actually 4. So the highest value and the amplitude don't need to be the same. Let's see what happens on this one. What would be the amplitude of 4 sine 3x? Yep.
Would it be 4?
It would be 4 because there's no vertical shift. When you throw in a vertical shift, that's when it can change this number and that number. Because there's no vertical shift, they will be the same. Okay, so amplitude is always the absolute value of the number in front. And period. Does anybody remember the formula to find the period? I think we used the letter T. It's T equals, and then we add a formula. Yeah, Lens?
T equals 2 pi over b.
Yes, T equals 2 pi over b, but what's b in this case? Yep,
3.
3. So the original cycle was 2 pi. We've now compressed that by a factor of 3. Okay, it's 2 pi over 3. All right, so let's graph it and confirm everything we just did. Okay, so first thing we want to do is make sure we are in radians. So if I haven't shown you how to do that yet, you press mode. It's the 4th row down, and we're going to make sure we are in radians. Go to y equals. Type in 4 sine 3x. And then there's a certain zoom that we can use when we're graphing trig functions. Anybody remember what zoom I said we're going to start using more? When we're graphing trig? Yep.
5, like the square one.
So square is good if you want things to look proportional. But it actually, that would not be good for a trig function. I don't even know if we would get a picture that you would see. Yeah, it's just going to look like kind of a straight line. Yeah. Zoom 6 also is not going to look that good here. Yeah.
Zoom 7.
Zoom 7. That's going to look a lot better. That's just barely okay. I would probably set the Y min and max a little higher. But Zoom 7 defaults to -4 to 4 on the Y, which is exactly enough for the range. Okay, so let's make it a little higher. Let's make it like -6 to 6. And now we can definitely see that it's not going off the screen. I mean, I think we could before too, but that's even clearer. Okay. They didn't say how many cycles they wanted us to show. We're showing several cycles there, maybe 6 or 7 of them. And that's fine. Okay. So the window that we used, -6 to 6 on the Y. And whenever you do Zoom 7, it's going to do this -8.6 number. I think in degrees, it's about 450 degrees, I think. How do we change degrees to radians? What do we multiply by? Yep.
The pi over 180.
Yep. Let's do times pi over 180. So that's 7.8, and that was 8.6. No, actually, it's even bigger than 450. I don't remember what it is. That's just what they use. Okay. Any question on that one? All right. Let's do the same thing here. Find the graph, and then domain, range, period, amplitude. Okay. What's the domain of 3 sine, and then in parentheses, x minus 1? Yeah.
Negative infinity, positive infinity.
Yep, all real numbers. -infinity to infinity. Okay, so there's our domain. What's the range? 3 to 3. Amplitude, let's do that. Okay, what's the amplitude going to be? Yeah, Jackson.
3.
3, good. And the period. Yeah.
2 pi over 1.
2 pi over.
2 pi.
In this case, there's just a 1 in front of the x, so there is no change to the period. 2 pi. Okay, so now I want you to graph it this time, but I want you specifically to show me exactly 2 cycles. I don't want more, I don't want less, I want exactly 2 cycles. So let's put that in. 3 sine, oops, 3 sine x minus 1. Okay, how long is one cycle of this graph? Yeah.
That'd be 4 pi.
One cycle.
2 pi.
2 pi. So how long would 2 cycles be?
4 pi.
4 pi. So if I want to show 2 cycles, that means I need a window that is 4 pi wide. You can set that any way you want. You could go 0 to 4 pi. You could go 4 pi to 8 pi. You could go negative 2 pi to positive 2 pi. As long as when you subtract the x min and the x max, you get a 4 pi, you've got something that's 4 pi wide. I only have to go negative 3 to 3 on the height. I'm already all set with a negative 6 to 6. So this should show exactly 2 cycles. There's 1, and it should end right about up there. There's 2. 2 full cycles. It doesn't look like the traditional sine graph because we have shifted it 1 unit to the right. Any question on that one or the window that we used? Okay, the other, yes?
What exactly is a cycle? Like, is it one of the humps?
Yeah, so a cycle is just, if we're looking at it here, it would start right here, and it would stop right about there. That's one cycle. And then if I took this and I copy and paste it again, that's another cycle. So that's 2 cycles. The other thing that you can do is when you type in on the window, and you probably noticed it, you can type calculations in, and it'll figure them out for the x mins and x maxes. So if you type in 4 times pi, and then you press an arrow, it will calculate what 4 times pi is. Okay, so you can put any kind of calculation you want, and it'll do the math out. Okay, so we've looked at the graphs of sine and cosine, and one of the very first things I did was I showed you both, and I asked you, look how similar sine and cosine look to each other. And we realized that sine and cosine are pretty much identical. The only difference is they are horizontal translations. So if you graph sine and you graph cosine, there's sine and there's cosine. Pretty much the same thing. But if you took sine, which is the graph in blue, and you shifted it pi over 2 units to the left. So move that right there. Shifting sine pi over 2 units to the left will turn it into cosine. Or you could take cosine and shift it pi over 2 units to the right. And that would turn it into sine. So anything that you have to do in trig with sine and cosine, you could just do with one of them. You could just do everything with sine. There's really no need for any other trig function. We don't need tangent, cotangent, secant, cosecant. It might start to look kind of messy, but you could do everything in trig with just sine or cosine. But we have other trig functions because then it doesn't look as messy, and it's a little bit easier to do. Okay, so those are called horizontal shift identities. Any questions on that? What would pi over 2 be in degrees? Yep. 90 degrees. So what we say is that sine and cosine are 90 degrees out of phase from each other. They're 90 degrees out of phase. Okay. So next thing we're going to look at is solving a trig equation on the calculator. So let's just think about what happens if you set a trig equation equal to a number. Here's a trig equation. Something like that. Now, if we set that equal to a number, let's say you put just a single number in y1. What does it look like when you put a number in y1 and graph it? Yeah.
You'll get a horizontal line.
Right, you get a horizontal line. And now let's assume that you graph a horizontal line somewhere between -1 and 1. Not above or below the graph. Somewhere like that. If you graph a sine function and you graph a horizontal line, how many times will they intersect? Assuming that it's within -1 to 1. If the horizontal line is above it, then they don't intersect. But if it's between -1 and 1, how many times will they cross? Yep.
An infinite number of times.
Right, an infinite number of times. Okay. In fact, this particular one is crossing twice per cycle. This is exactly the same as that. The difference is this one is one cycle later. This and that are the same answer. Okay. The difference is that is one cycle later. So when we are finding answers to trig functions, it's impossible to write down every single answer because there's infinitely many. But what we can do is find the first, in this case, just the first 2 answers, and then say that those 2 answers keep repeating every cycle. That's all we have to do. Find the first 2 and say that they repeat. If they ask us to write all solutions, if they ask us to only find solutions in a given interval, then we don't have to worry about saying that the answer repeats. All we have to do is set the window on the calculator to go between 0 and 2 pi and literally calculate every single intersect from 0 to 2 pi. But this idea of understanding that even if you're only looking at this, knowing that these answers are going to repeat again later on, that's important. That's how we're going to be writing all our answers in the future. But for now, we'll just find the answers in that window. Okay. Notice how they wrote the window. If you were going to write this in interval notation instead of an inequality, could somebody write that for me as an interval? Yeah.
Close bracket 0.
Yep.
And open parentheses 2.
Right. You don't include both ends of the interval. The reason is when you are looking at your screen, if I put in something like, let's just do sine x, and let's graph from 0 to 2 pi. Why wouldn't I include both edges of the screen? Why is one included and one is not? Yep.
Because it would be the start of the next interval, so your point at 1 could effectively be the same as the point. Well, the point at the beginning of the interval will effectively be the same as the point at the end of the interval.
Right. This is exactly the same as that. It's just that is one cycle later. So that's why when you are setting a window to one period or one cycle, you don't include both edges of the window. Generally, they include the left edge, not the right. That's how they do it. Okay. So let's find our solutions. Now, there's several ways to do this. Okay. One way to do a problem like this is to do this. Okay, I haven't taught you that yet. So we're going to eventually look at that. That used what we call inverse trig. And I would also have to do this. And I haven't explained why I would have to subtract 0.41 from pi. There's a reason. Not something I'm going to get into right now. My point of showing you that is I wanted to demonstrate how fast I can do that problem without graphing anything. Okay. Now, we're going to do it graphically. Okay. Not as fast, but graphically, there's less you have to understand. Okay. You don't have to understand why I subtracted something from pi. You don't have to understand what is this -1 thing mean, this inverse trig. What's that? Okay. We're going to talk about it, but we're not going to get to this today. Okay, but just remember these two numbers and how quickly I was able to get them. All right, so now, let's graph this. We're going to put sine of x in y1. We're going to put 0.4 in y2. There you go. So sine of x, 0.4. They said to set the window from 0 to 2 pi. I'm all set, 0 to 2 pi. And because this only goes -1 to 1, I wouldn't worry about -6 to 6. Let's do -3 to 3. Okay, and what is it that I have to find now, looking at that picture? Yep.
The intersections between the two,
Yep.
between the waving line.
So yep, we're going to find the two intersections. Remember, if you just do intersect and hit it, there are two of them, but you'll get one of them randomly, whichever one you were closer to. And I got 2.7300758. That's exactly what I had on this screen. 2.73. In fact, it was the second answer. Okay. Took a lot longer to do it graphically. I had to type it in, set a window, do an intersect. Took a lot longer. All right. Now, let's do the same thing again. But how do I get the second one? Or in our case, the one on the left. How can I make sure the calculator gives me that one? Yeah.
Use the arrow keys to bring yourself closer to the leftmost point.
Right. I got to get a little bit closer. That should be, as long as I'm beyond halfway closer, that should be fine. And I get 0.4115165, and that's the other one that I had right there. Okay. So there's definitely more than one way to do this, but graphing is how we're doing it for now. They will generally tell you to write your answer to a certain number of decimal places. If they don't, let's do 2. So x equals 2.73, x equals 0.41. Any questions on that? All right. I think I wrote that backwards. Let's try this one. Okay, so we've got a cosine graph, and we've got 1.5 on the right. Now, what's the highest and lowest that cosine normally goes? Just the original. No modifications. Yeah.
-1, 1.
It normally goes -1 to 1. So does that mean we can automatically just say, oh, no solution? We're trying to find where it hits 1.5? Is that just going to be above the whole wave? You think, Travis?
No.
No, why not?
Is it multiplying by 2?
Yeah, this isn't a regular cosine function. We doubled the height, so we will hit 1.5. Okay. All right, so let's set up our window. So 0 to 2 pi is pretty common. So a lot of times, once you set 0 to 2 pi, you might not have to change it for quite a few questions. We're going to put in 2 cosine. Now, if I was doing this, I would put in 0.5x, because then I wouldn't have to deal with an extra set of parentheses. But if you get a fraction, like 7/13, that's not a nice decimal, you are going to have to do it as a fraction. So this is one way you can do it as a fraction. 2 cosine 1/2 x. You don't want to type it in as cosine 1 over 2x, because the calculator will think you want this. You don't want that x in the denominator. Okay. So by putting an extra set of parentheses, I avoided that problem. Okay, and on y2. Layla, what am I going to put on y2? Yep, I'm going to put the 1.5. Okay, got our window, we got our equations. Hit graph. And this time it doesn't hit twice in the screen because the 1/2 stretched it out. We stretched it out so much we didn't give it enough time to come back. Okay, it comes back off the screen. So this only has one answer in the screen they want me to look at. So this time the guess doesn't matter because there's only going to be one answer, so I can just hit enter, and I get 1.45. Okay, also notice I'm doing all these in radians. Okay, you know you're in radians because it says radians at the top. If they don't say the units, we always want to stick with radians. But this is telling you the units. Okay? They're telling you x is between 0 and 2 pi. When you solve for x, you are solving for an angle. If they wanted this in degrees, they would have had to do that. They would have had to put a degree symbol. So make sure you pay attention to any constraints they give you in the problem. If you see degree symbol, you need to change to degrees. Okay. And remember, when you change the mode, it's not just going to mode, changing to degree, and hitting graph. A lot of people get something like that, and they're like, why did my wave turn into a straight line? Well, you not only have to change the mode, you have to change the window. Okay? If you want to do this problem in degrees, you shouldn't be going from 0 to 6.2. What should we be going to for an x max if we're doing it in degrees? Yeah? That's more than 90. 90 is pi over 2. 360. So if you want to get the exact same picture, you got to change the mode and you have to change your window. Now you've got the exact same picture. Okay. Any questions on that one? Let's do one similar to that. Let's do this one. Let's do sine of x equals 0.5. And I want the exact answer in radians. So exact answer means I don't want a decimal. Unless it's a decimal that terminates, that's fine. But if it doesn't, I want it exact. Okay, so what? Let's just start out about Marcelo. What would be my first step?
Well, like writing the equation into the calculator.
Sure.
With the sine x.
Okay, so let's put in sine x. Got that. What next?
You have to put in the 0.5 in the next line.
Okay, so let's put in 0.5. Okay, and I'm going to use the same. So let's go from 0 to 2 pi. So same window, so we don't have to adjust that. And now I've got everything typed in. My window, actually I do need to change it back to radians. Now I'm ready to graph it. Okay, and Gregory, what would I do next?
Adjust the graph.
What are you thinking you want to adjust?
Like the x-axis.
Okay, so we've already adjusted that to be 0 to 2 pi. I did that in the window and when I changed it back to radians.
You could lower like the y-axis and I guess.
You want to look lower?
No, like condense it, to like so you can zoom in, I guess.
We could. I mean, there's a little bit of space we could zoom in, but I can see pretty well that it's a wave, and I can see the red line. So I don't really need to zoom in too much. It's big enough, I would say. So what is it? What do we do now?
To calculate points of intersection.
Right. Let's do the intersection points. Let's do this one right here. 2.6179939. Okay. If I write that down, is that an exact answer? No. What if I somehow could get 20 or 30 more decimal places? Would that make it exact? No. More decimal places doesn't mean it's exact. It's more precise, I guess, but it's still not exact. So what am I going to do? How am I going to get an exact answer? Yeah.
Subtract it by pi. Subtract pi.
You could try. I'm not sure that would help you to get an exact answer. Yeah, I think it'd still have a decimal that's kind of a long decimal that would be annoying to work with. How else could I do this problem still on the calculator besides the mode that I did it in? Yeah. Let's do the problem in degrees. Okay. If you're going to be able to if you have to find an exact answer, then it needs to come out to a nice number. If it's going to come out nice, it will come out nice in degrees. So let's change the mode to degrees. What should I change my x max to so it's equivalent? Yep.
360.
360. Okay, I'm going to get the same picture. Now remember, they still want the answer in radians, but this is going to help. Let's do second calc intersect. And I get 1/5. So I get a nice answer. What could I do with that 150 now? Yeah.
Multiply by pi over 180.
Right, convert it to radians yourself by hand. .30 goes into both. That is 5 pi divided by 6. Let's type that in and see if that 5 pi divided by 6 looks familiar. 5 pi divided by 6, 2.61799. Okay, if you remember, that's exactly the number that I had when I did it in radians. But now I have the exact answer. Okay, so that's the trick for how you get an exact answer. You have to do it in degrees first, convert to radians by hand. Okay, other one is exactly the same concept. Do it again, you get 30 degrees, which in radians is pi over 6. Okay, there's too many decimals with pi to memorize every one of them. I mean, it's 5 pi over 6, you have 13 pi over 6, you could have 14 pi over 2. You know, you get all kinds of decimals with pi. So this is how you do it. Okay. Any question on that? All right, and the last one. What's different about that one? Still going to use the calculator, but it's not the same kind of problem as the last 3. Yeah? It's an inequality. So when you write your answer here, you don't have x equals and then just a single number. How do we usually write our answer to an inequality? Yeah?
As an interval.
As an interval, exactly. So you're still going to have to find intersection points, but now your answer is going to be an interval, not x equals a number. Okay, so let's put it in. We've got 2 cosine x. We've got negative 1.3. If it weren't for this 2, we wouldn't even hit negative 1.3. But this is going to stretch it, so we will. Okay, and they want 0 to 2 pi, so that's fine. Let's also go back to radians. Okay, they didn't say anything about exact answer in this problem, so I'm not worried about doing it in degrees first. Where is that inequality satisfied? Can you explain to me, like, what am I looking for in this picture? Looking for where what happens. Yep.
A value is above the red line.
Right, I want the cosine value to be above the red line. Well, that happens in 2 different regions. Happens in that region. And it happens in that region. So there are 2 different regions we're going to have to write. As long as your x value falls somewhere in region 1 or 2, it is an answer to the question. Okay, let's start with region 1. Where does region 1 start? X value. Yep.
At 0.
At 0. Can I include or don't include 0?
Include
Why?
because it's more specific.
Well, the only reason we can include or not include something is because of information in the problem. So there is something there that tells you you need to include 0. You don't have a choice. Yeah?
The problem states that we're looking at values that are greater than or equal to 0, so
Right.
we include 0.
It says you need to include the left edge of the screen, greater than or equal to 0. So interval 1 is going to start at 0. I don't know where it's going to stop. It's going to stop right about there. Can I include or do I not include where interval 1 stops? Yeah?
You don't include it because it just said it's greater than negative 1.3.
Right. I have to be above the red line. I cannot equal the red line. So we want to think of this as an open circle there. I don't know what it is yet, but I know I don't include it. Now we've got a second interval. Before I write the second interval, what symbol has to go right here? Because I'm about to write another section. Yep. Yep, union, which means or. So I can have an answer between these two numbers or these two numbers. Okay, interval 2. Don't know where it starts yet. I need to figure that out. Will I include or not include where interval 2 starts? Raj? Yeah, we don't include it. Same reason we don't include where interval 1 ends. So, don't know what it is, but I know I don't include it. And then, where does interval 2 stop? Lens?
What do you mean 2 pi?
Stops at 2 pi. Do we include or don't include that?
You don't include it.
We don't include it, because it says right here, you have to be less than 2 pi. You cannot go all the way to the edge of the screen. Okay, so that's kind of the structure of our answer. Now we just have to figure out where does interval 1 end and where does interval 2 start with the intersection points. And that's the same as what we've done before. So let's do second calc intersect. So interval 2 starts at, well, we'll call it 4.00. If we're rounding to 2 decimal places. And interval 1 ends 2.28. And that's how you write your answer to an inequality. Okay, so graphical, that's the focus for today. But keep in mind, there are many other ways to do this that are not graphical and usually faster. But they require you to understand some more things that we'll talk about later in the week. Okay. All right, so that's homework for tonight on page 346. We will take a look at that first thing tomorrow, and then we will look at section 6.4, which is all the other trig functions. We don't go into as much depth graphing the other trig functions. Okay, so we'll take kind of a quick look at